Hello and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll explore parallel computing on CPU cores using OpenMP, Open Multiprocessing, on the Fram Linux cluster. In our previous video, we looked at a Fortran program for matrix multiplication with OpenMP and its corresponding Python testing script. To begin our matrix multiplication testing, we'll start with a matrix dimension set to 8192. This will serve as our initial benchmark as we explore the performance of our algorithm across different problem sizes. Ensuring that we set the value of n to 8192 in our Python testing script is crucial for obtaining precise performance calculations. To simplify our process, we use the alias Intel to access the latest Intel Fortran compiler and the alias matplot to access the newest versions of matplotlib and NumPy modules. This setup eliminates the need to load each component separately, making our workflow more efficient. We switch to the standard compute nodes using our setup Python script. Here, we'll ask for one node with 32 cores to run our OpenMP tests. Also, we'll instruct our interactive job to wait in the development queue. It's crucial to compile and execute on the same compute nodes. Doing so prevents potential issues arising from architectural differences between login and compute nodes. After a short wait, we'll find ourselves redirected to the C85-6 node, where we'll proceed with our multi-threading tests using OpenMP. We'll initiate the testing phase by executing our Python script designed for testing purposes. Once launched, this script will trigger the commencement of our testing procedures, allowing us to gather valuable data and insights into the performance of OpenMP. Initially, the Python script displays the compilation command before proceeding to execute it. This deliberate action serves to provide transparency in our workflow, allowing us to review the compilation instructions. We'll examine the executable program using different thread counts for testing. This allows us to evaluate its performance across various thread configurations efficiently. In this test, we observe a significant speed-up when transitioning from 1 to 2 threads, with an approximate increase of 1.96 times in performance. This notable enhancement highlights the effectiveness of parallelization employing few threads with OpenMP. Next, when progressing from 2 to 4 threads, we observe a speed-up of approximately 1.78. Transitioning from 4 to 8 threads, we observe a speed-up of 1.71. As we increase the thread count from 8 to 16, the speed-up decreases to 1.63. The speed-up significantly decreases from 16 to 32 threads, dropping to 0.92. This drop indicates a slowdown compared to the performance achieved with 16 threads. It highlights the diminishing returns and possible inefficiencies of increasing thread count excessively. Our Python testing script uses matplotlib to generate plots showing the relationship between wall time, CPU time, and the number of threads used by the executable program during matrix multiplication. The plot, saved as time, PNG, can be copied to my iMac using the secure copy command explained in our previous video. By examining this plot, we gain valuable insights into the performance characteristics of our program. By plotting these metrics against the thread count, we gain a clearer understanding of how our program scales in terms of both time efficiency and CPU utilization. Note that we are employing a logarithmic scale on the time axis to improve readability. Let's start by showing the wall time values in the figure. This allows us to visualize the time taken by the program to complete its tasks as we vary the number of threads. Following that, we'll proceed to present the CPU time values. It's crucial to understand that multiplying the wall time by the number of threads employed derives CPU time. This represents the theoretical CPU time deducted from your CPU quota. We display this CPU time in the figure to demonstrate how thread count affects CPU time consumption, as wall time does not directly inform CPU time deduction from your quota. In addition to the wall time and CPU time values, we'll incorporate the speedup values to finalize the figure. It's notable that multi-threading demonstrates good performance up to 16 threads. However, there's a slowdown when transitioning to 32 threads. This observation underscores the importance of optimizing thread count for efficient parallel execution, as excessive threading can lead to decreased overall performance. Considering the short wall time observed for 16 and 32 threads, it might be worth investigating scaling up the matrix multiplication dimension to 16:384. This adjustment is anticipated to expand the computation time approximately eightfold. By increasing the problem size, we can further evaluate the scalability of our parallelization approach and assess its performance under more demanding computational tasks. To ensure precise performance evaluations, it's essential to update the value of n in the Python testing script. With our setup Python script, we transition to a standard compute node, C85.6, from the login node. Here, we'll proceed with the multi-threading test, setting n to 16.384 on this normal compute node. We'll start the testing phase by executing our Python testing script. The Python script first shows the compilation command and then executes it. We'll use the executable program and testing it with different thread counts. In this test, we see a notable performance improvement as we shift from 1 to 2 threads, nearly doubling the speed with an approximate 1.98 times increase. Moving from 2 to 4 threads results in a speedup of about 1.78. The results for the other thread numbers will not be shown here, but they will be included in the figure generated with matplotlib. We'll plot both wall time and CPU time using a logarithmic scale on the time axis to enhance clarity. Let's start by showing the wall time values in the figure. Following that, we'll present the CPU time values. We'll include the speedup values to complete the figure, in addition to the wall time and CPU time values. Up to 16 threads, multi-threading shows promising performance. However, transitioning to 32 threads emphasizes that excessive threading can reduce overall parallel computing performance. Let's do one more test with n set to 16.384. To enhance performance, we'll activate multi-threading in the program's initial loop, enabling parallel execution across the entire program, ensuring parallel execution of all its components. Using our setup Python script, we move to a standard compute node, C8512, from the login node. Here, we'll conduct the multi-threading test, setting n to 16,384 on this normal compute node. We'll begin the testing phase by executing our Python testing script. The Python script displays the compilation command before executing it. The script will test the executable program created by the Intel Fortran compiler with different thread counts. We've incorporated OpenMP directives for both loops in our Fortran program. In theory, we anticipate achieving a perfect speedup of 2, given that all program parts can execute in parallel. However, as we'll observe, this ideal outcome isn't realized in practice. In this test, we witness a substantial performance enhancement as we transition from 1 to 2 threads, almost doubling the speed, with approximately a 1.99 times increase. Going from 2 to 4 threads results in a speedup of about 1.83. The results for the other thread numbers will not be shown here, but they will be included in the figure generated with matplotlib. Let's examine this test by looking at the plot that shows both the wall time and CPU time on a logarithmic scale. Let's begin by displaying the wall time values in the figure. Afterward, we'll display the CPU time values. To complete the figure, we'll add the speedup values to the wall time and CPU time data. Initially, multi-threading performs well up to 16 threads. However, transitioning to 32 threads reduces the speedup to 1.42, even with all parts of the program executed in parallel. We'll conclude our investigation on the Fram Linux cluster with a plot showing the performance in gigaflops based on CPU time, C second, and wall time, W second, for the final multi-threading test. In this test, all parts of the program were executed in parallel. Our findings suggest that using more than 16 threads may not be advisable. However, we'll discuss methods to improve multi-threading parallel computing performance using OpenMP affinity in upcoming videos. In our upcoming video, we'll explore multi-threading on the Betsy Linux cluster, experimenting with up to 128 threads. Join us as we uncover valuable insights to deepen your understanding of parallel computing with OpenMP. I am looking forward to the next video, wishing you all happy computing in the meantime.